So this is a SciArm PT seminar, and it's my great pleasure to introduce Professor Eduard Feireisl from Prague. He is the academic member and senior researcher in Czech Academy and professor in Charles University. And so today I saw Masainet, and he has been written 365 papers, and his total citation is 7,279. And everyone knows that he is very outstanding mathematics in PDE, in particular fluid mechanics. And today he is going to talk on dissipative system in fluid mechanics. So Eduard, please.
Thank you very much, Hideo. First of all, I would like to thank Anna and other organizers of this webinar that they gave me this opportunity to present some results that, as I pointed out, that they are not directly related to some publication in CIMA. However, they feature some common aspects with some of my publication in CIMA. So I think finally they will do I will do some kind of presentation anyway. So this is about dissipative system in fluid mechanics. There will be many co-authors that I will mention during my talk. So let me start. I mean, actually I say systems, but there will be only one system. Let me start with some kind of a motto for my talk. Actually, there are, at least in my opinion, two basic problems in the long-time behavior, say, of systems, of solutions of systems of equations in fluid mechanics. The first one concerns closed systems. By a closed system, I mean a system that does not exchange mass, neither mass nor energy, with its neighborhood. And I must say, mathematically speaking, these systems are very boring. As we will see, they basically obey what is stated as a kind of pessimistic formulation of the second law of thermodynamics due to Clausius, which means the energy of the system remains constant since the system is isolated, so there is no way to exchange energy, while the entropy of the system will converge to a maximum. And this is indeed something we could really prove, and you will see for one specific system arising in fluid mechanics. So from this point of view, the scenario is not very exciting since everything tends to equilibrium. What is more, as we know, systems in fluid mechanics are mostly nonlinear. And so the fact that actually they remain close to equilibrium gives you the possibility of, say, linearizing the system and obtaining results about the existence of regular solutions by means of some perturbation, because the equilibrium is usually regular. And on the other hand, the real systems, I mean, systems that we can observe in nature are open systems. They exchange mass or energy with the neighborhood, and this is formulated in mathematics by imposing several types of boundary conditions. I put a picture of Clausius. I was not sure what I should put, whom I should advertise, like whose work I should advertise most. And finally, I found that maybe the most, I would say, prominent guy who contributed to the theory was Kolmogorov. So I'm presenting his picture of, although the statement which is on the screen is not really attributed to him. Open systems, as I said, they exchange mass and energy with the neighborhood. And so the long-time behavior or asymptotic behavior is more interesting, and there's the celebrated ergodic hypothesis, which means that actually we can take long-time averages of separate trajectories, and their joint behavior should be characterized by certain probability measures sitting on the phase space. I will try to show you some kind of proof of this statement, again, in the case of very simple system. And of course, the proof, as you will see, will not be very satisfactory. What is peculiar to open systems is that they live out of equilibrium. So normally you need, mathematically speaking, you cannot rely on any perturbation theory. So typically, even the question of the existence of global in-time solution is non-trivial. And the only framework available so far is the framework of weak solutions. So I will speak about weak solutions to some problems in fluid mechanics. So that's the long introduction. Now let me present the system. The system, although it looks like not very simple, is the simplest possible, I would say, system in fluid mechanics where you take into account all three basic physical principles, which is the mass conservation, momentum balance, and internal energy balance. So let me explain the meaning, maybe for those who have never seen this. This is usually called Navier-Stokes Fourier system, and it's a system that describes the motion of a general compressible, heat conducting, and viscous fluid. So this is the so-called real fluid, where viscosity is always present and heat conductivity is always present, in contrast with the idealized Euler system, where this is not the case, and it's a mathematically very different object. So the meaning of this equation, the first one is just mathematical formulation of the mass conservation. There are two unknowns, which is rho, which is the mass density of the fluid, and u, which is the fluid velocity. And there is one more, which is the temperature. Usually in this context, we speak about the absolute temperature with respect to the Kelvin scale. And so the second equation is Newton's second law, which is actually the momentum balance, where there is a new function appearing on the left-hand side, which is called pressure, which is a function which depends on the density and also on the temperature. And on the right-hand side, there is one term which represents some kind of external force. Typically, the external force is in the form of a gradient of some potential, and in most of cases, I know the external force is simply the gravitational force acting on the fluid. But there is also the viscous stress or divergence of S, which represents viscosity, and as we will see below, I have chosen the simplest possible case of viscous stress, which is the which is a tensor which depends in a linear way of the symmetric part of the viscosity gradient, and such a fluid is called Newtonian. Well, the system, so far we have like two equations, but for three unknowns, which is rho, u, and theta. So you have to add something more, and something more is the representation of the first law of thermodynamics, which in this context, the most convenient way how to write it is the so-called internal energy balance, or if you want the heat equation, which is the last equation here. There is a new quantity, which is the so-called heat flux vector. And there is a heating term which represents which is due to viscosity, and there is a pressure term which somehow makes sure that if you take the first equation like momentum balance, you take the scalar product with this equation and the function u, which gives you the kinetic energy balance, then you will find out that these two terms, which represent the pressure and the energy, will completely cancel, and you will end up with a total energy balance. However, for this system question, it's much better to work with the internal energy balance. And so, as I said, I assume that the fluid is Newtonian. So the viscous stress depends in a linear way on the symmetric part of the velocity gradient. It is convenient to write it as a sum of two components. The first one is just the traceless part of the symmetric velocity gradient, which is called shear viscosity, and the coefficient in front is the so-called shear viscosity coefficient, plus another component which is called bulk viscosity, which is as a diagonal vector. It's just similar character to the pressure, and it's multiplied by the bulk viscosity coefficient. In some models, the bulk viscosity is completely omitted, which means that you can assume that the eta is actually equal to 0, which is the so-called Stokes hypothesis. Well, the heat flux, and this is where the name Navier-Stokes Fourier comes from, is determined by the Fourier law, which is simply this one. Again, it's a function, it's a linear function of the temperature gradient, and the coefficient is called heat conductivity coefficient, and I will assume that that is always positive. Actually, in my talk, the heat conductivity coefficient as well as the viscosity coefficients at some part will be also functions of the temperature. Okay, so this is the system. The system is conservative because it conserves energy, but whether or not it is closed or open depends on what kind of boundary conditions you want to impose. But let me first continue a little bit with mathematics, with equations here. So we have seen there is a function P, which is the pressure, and there's a function E, which is the internal energy. And I suppose a little bit more. I suppose that the validity of the second law of thermodynamics, which sometimes is stated in the form of Gibbs law, which says basically that if you take differential of these functions, of the function E and of the pressure time, the differential of 1 over rho, I mean, this 1 over rho looks a little bit mysteriously. However, the physical meaning of 1 over rho is just a specific volume here. And so the Gibbs law postulates that there is a new function called entropy, such that if you divide the expression on the right-hand side by theta, you get a perfect differential, and it's a differential of a new function, which is called entropy. And if this is true, then you can derive easily from the last equation, I mean, from the first and last equation on the previous slide, that actually the entropy is formally conserved. And this can be seen as a mathematical statement of second law of thermodynamics. I mean, conserved in the sense, I would say balanced, in the sense that it satisfies an equation here. The equation is not a new equation. It's something that you can deduce from the previous three equations. However, that's true in the context of smooth solutions. Later on, I will speak about weak solutions, and in that case, the entropy balance must be postulated as an extra equation or even inequality, but we will see later how this can be done. On the right-hand side, I say entropy conservation, which is not really exact. Actually, entropy is not conserved. On the right-hand side, you see a term which is called entropy production rate. The entropy production rate is non-negative, as you remember, because Q is minus kappa gradient theta. So both terms here can be shown non-negative. So this means that the entropy is actually being produced in accordance with the statement of Clausius on the first slide. So actually, this entropy balance equation, although it may look like a secondary equation, is quite important because it will be used later as one of the leading equations in the weak formulation of the problem. Finally, I will also assume that the system, or actually the constitutive relations, comply with the principle of thermodynamic stability, which can be expressed in many different ways. One of them is, for instance, that the pressure is an increasing function of the density, while the internal energy is an increasing function of the temperature. I prefer to write it in this way, which is completely equivalent. I write the total energy of the system, but I write it in terms of new variables that are sometimes called conservative variables, which means rho, m, which is momentum, and s, which is the total entropy. And so that's the total energy of the system now. And thermodynamic stability actually is equivalent to saying, or if you want, it's a definition of thermodynamic stability, is that this function is a function of m rho and s is strictly convex. And so that's what I will always assume in my talk. Okay, so I should speak about boundary conditions. So let me start with conservative systems. In the conservative case, just to show you that conservative systems actually have a lot of nice properties. Actually, they are mostly studied in textbooks. In textbooks, you usually find a system that is conservative, which means the physical domain, I assume that the fluid occupies a bounded domain, and well, I mean, everything can be done, of course, in 1, 2, or 3 space dimensions, but the most relevant case, and I will focus on it, is the case when d is equal to 3. And then the conservative boundary condition, the first condition postulates that there is no mass flux through the boundary, which means the normal component of the velocity is 0, which immediately gives rise to the total mass conservation, which means that the total integral of the density, which is the total mass of the fluid, actually doesn't change in time. Secondly, you can also assume, so typically this condition is accompanied with the condition that the tangential component of the velocity is 0. And so you end up with a so-called no-slip boundary condition, which in particular seems to be physically relevant for viscous fluids, which simply tells you that the velocity on the boundary is 0. Then if you want the system to be thermally conservative, you also prescribe the heat flux on the boundary, at least its normal component, to be 0, which gives rise to the conservation of the total energy. The time derivative of the total energy is equal to 0, exactly again this Clausius statement. The whole energy, the total energy of the system is conserved. It doesn't change in time. And from the entropy equation, you get this equality, which means that the time changes of the total amount of entropy are proportional to the integral of the entropy production, which is non-negative. So this is an increasing function. And these three relations are the only source, I would say, of a priori estimate for the Navier-Stokes-Fourier system. So if you think in terms of weak solutions, the only information you will get is that, well, rho is bounded in L1 because rho is always non-negative. So this tells you that actually you control rho in the L1 norm in terms of the initial data. This estimate tells you that you also control the energy in terms of the initial energy. But as we know, if I express the energy as a convex function of rho n and s, this gives me also some control over rho n as s. And finally, since you can also show that the energy somehow dominates the entropy here, you can also show that this term here is actually, at least its integral is bounded. And these are the only a priori estimates you have at n. It looks like it's not so much. However, in contrast, but it will be much worse for the open systems where this is not even available and you have to do something else. Well, if you have this estimates at hand, you can show, and this can be even shown for the weak solutions. I will not specify now what I mean exactly by weak solutions. Later on, we will see what I mean by weak solutions for the open systems. But here, what can be shown is that the following actually statement, which is in perfect agreement with Clausius' second law, or with Clausius saying on the first slide. So assume that you have a global in time weak solution of the problem, then what you can show is that actually when times go to infinity, the density approaches some state rho s. I'm not saying in which sense it's usually in some LP norm, but there is a convergence at least in some LP norm, where P is somehow related to constitutive equations. The temperature converges to some limit temperature and the momentum converges to zero. And the limit density and the limit temperature satisfy this equation, which is actually what remains of the momentum equation. If you set u equal to 0 everywhere, there's a so-called static equation which characterizes the state of the fluid that is not moving. The velocity is equal to 0, which means the gradient of the pressure is equal to rho s times the gradient of the gravitational potential. If you want, this equation may have a lot of solutions actually. But we also know that the total mass is a constant quantity, and under certain conditions imposed on the pressure, in particular, the pressure is of type of Boyle-Mariotte law. You can show that there is a unique solution which complies with this condition. So actually, when time goes on and when time goes to infinity, any weak solution of the problem approaches an equilibrium state. So that's not so exciting. Now let me switch to more exciting kind of boundary conditions. I say I would like to consider open systems, but I will focus on open systems in terms of thermal energy, or in terms of total energy. So I will skip the case when the velocity is given on the boundary and it is not zero, which would of course bring some extra difficulties, because in that case you have to also to prescribe the density, and on at least on the part where the velocity is so-called, where there is the so-called inflow condition. But I will not do that. I will just simply assume that the velocity is equal to 0, but we will still see that there is a lot of interesting phenomena going on. If you simply change the Neumann condition, which was the condition that the heat flux is, or at least its normal component is 0, to the so-called Dirichlet boundary condition, you prescribe the value of the temperature on the boundary. An iconic example of such a situation is the so-called Rayleigh-Bénard convection problem, in which case the domain omega is just, unfortunately I don't have any picture, but in that case the domain omega are just two parallel plates where the temperature is prescribed at the bottom and the top, and the temperature at the bottom is higher than the temperature at the top. And if in addition you put in action the gravitation force, then when the temperature gradient, meaning the difference between top and bottom temperature, is high enough, you can see some patterns forming on, and these patterns will survive. The system will not stabilize to equilibrium, at least not seemingly, and definitely not to equilibrium, or in the general not to equilibrium with constant velocity, because there is a simple example. There is a simple proof that actually static equilibrium, which is equilibrium solution with constant velocity, may not exist for such a simple system as soon as you prescribe a boundary temperature. And the proof is very simple. You go back to the equation and you assume that you have such a solution. So you assume that the velocity, that there is a solution for which the velocity simply vanishes. So you try to find the like thermostatic equilibrium of the system. If the solution vanishes, then you go back to the internal energy balance, and you will see that actually the temperature, the equilibrium temperature must satisfy this equation here, which is nothing other than like a Laplace equation, where modulo some coefficient. Assuming this is constant, you will get nothing other than Laplacian of theta s is equal to 0. And in addition, you have Dirichlet boundary condition. As we know, this problem has a unique solution, which is uniquely determined by the value of theta b. So there is nothing to do with this unique solution. Then going back to the momentum equation, you end up with this equation for the pressure, which is exactly the same as before. You take a curl of this equation, because the left-hand side is a gradient, the curl is 0. If you are careful, you can compute also the curl of the right-hand side, which tells you that actually the gradient of the static distribution of the temperature must be parallel to the gravitation, to the gradient of g, which is the direction of the gravitational force. If you write this in terms of rho and theta, you will end up with this, and taking the vector product with rho s, you will end up, sorry, with theta s, you end up with this condition that actually the gradient of the temperature, of the equilibrium temperature, must be parallel to the direction of the gravitational vector. But now you see, since the equilibrium temperature is already determined by this equation, it may very easily happen that this is not the case. I mean, in particular, in the Rayleigh-Benard convection problem, if the gravitation is not exactly perpendicular to your plates, then this will never be the case. But of course, there are other problems that this is not the case. So for open system, when with the Dirichlet boundary conditions, there is simply no static equilibrium. So this makes the problem interesting, because then it means that the system is really moving out of equilibrium, at least out of static equilibrium. Well, so what is the problem? The problem now is to get a priori bounds, because since we would like to consider to construct solutions in some way, we need a priori bounds. We need some quantities that are bounded in terms of the data. And the system arises immediately when you write down the total energy balance. The total energy balance, unlike in the conservative case, is no longer the derivative of the total energy, is no longer 0, but it's proportional to the heat flux through the boundary, which for conservative, in the conservative case, this was 0, right? Now it is not 0, it's something we do not control, because we know what is the temperature on the boundary, but we don't know what is the heat flux on the boundary. So that's something we do not control. You do the same with entropy. So you write the entropy balance equation, but again, you end up with an extra term on the boundary, which looks very similar like this one, but is divided by 1 over theta. So you have neither energy nor entropy balance, so it looks like kind of hopeless case. However, what saves the situation is so-called the ballistic energy. The ballistic energy is a quantity which looks like the total energy minus theta times the total entropy, where theta is a prescribed temperature profile which coincides with theta b on the boundary. If you multiply the entropy equation by this theta, you will find out that this term will be actually capital theta over theta on the boundary, but since they coincide on the boundary, it will be 1. So it will be exactly the same as this one. So if you take the difference of these two problematic terms will disappear, and you finish with this expression, which is called ballistic energy balance for the Dirichlet boundary conditions. So you see, it looks very good, because again, you have something like time derivative of the total and of the ballistic energy. Now you have the dissipation term, which has a good sign. However, on the right-hand side, you have some expression which depends on the gradient of this theta, on the gradient of the extension of the boundary temperature. Well, if the boundary temperature is constant, this gradient is 0, and then you have no problem. You get basically some kind of dissipative principle for the ballistic energy. If this term is not 0, you are in trouble still with a priori estimates. And frankly, if you consider the case, which is the most popular one, which is the case when the pressure is given by Boyle-Mariotte law, which means rho times theta, and so the corresponding entropy is just log theta to CD, where CD is a constant over rho. then I don't know about any a priori estimates that would follow from this relation. So later I will show you what to do. Okay, so actually the remedy comes a little bit unexpectedly from taking a little bit more physics into account. So we know that we have Gibbs law. So now the question is how to choose my state equations. So a thermodynamic stability condition can be also expressed in this form, which means that the pressure is simply increasing function of rho and the internal energy is simply increasing function of theta. And then I take the equation of state in this form, where there are two components. The first one, Pm comes from molecular pressure, satisfies exactly the equation that should be satisfied by a monoatomic gas, which states that actually the pressure of the gas is given to 2/3 of the total internal energy. The second component is the so-called radiation pressure. This radiation pressure is added to it's a term which is normally very small since it is multiplied by what is called Boltzmann constant. However, it has a very important regularization effect in the construction of weak solutions. So I somehow need this term in order to construct the weak solutions. Otherwise, of course, I do not. The dream would be, of course, to forget this term, but unfortunately, so far I don't know how to do that. But let's look at this term. So the internal energy accordingly is then written in this. Now the Gibbs law tells me that if I have this the monoatomic gas state equation, this Pm is written down necessarily in this form, which looks a little bit mysteriously. There is a new function capital P, which can be whatever, arbitrary for the time being. And so you can observe that if this function is just a linear function, then this 5/2 will cancel with 3/2, and this will give you just rho times theta, which is the Boyle-Mariotte law. So I would say the correct choice here would be to take a linear function. However, as I said, for this we don't have any estimates. So the correct choice is given to you by physics, and in particular by the so-called third law of thermodynamics, which somehow postulates that the entropy, when temperature goes to 0, should not go to minus infinity, as it is the case for Boyle-Mariotte, but it should go to constant. And since the entropy is the term in modulo additive constant, you can assume that this constant is 0. Well, if you impose, if you postulate this, then you will get actually these conditions. So first of all, the thermodynamic stability for this function P gives you this. This is just a consequence of thermodynamic stability, which tells you in particular that P of Z over Z of 5/3 is a decreasing function, and we postulate it converges to some positive constant. Then the entropy is given in this form, is written in this form. This is the so-called radiation entropy due to the radiation pressure. And if you postulate this, you get some conditions on this P. And if you don't like, assuming some exotic conditions, you may think this is your favorite Boyle-Mariotte state equation till the moment when this quantity, which is sometimes called the degeneracy factor of the gas, is not very big. You can take P to be linear up to a very, very big value of this Z here, and then you do something. You modify it, because for big Z, the gas already, or the fluid already does not behave according to Boyle-Mariotte law. And these two conditions actually surprisingly give you a priori bounds for the system, and they give you much more. Okay, so to make this long story short, assuming also some conditions on the viscosity in particular, I assume that all transport coefficients depend on the temperature. We have some solid basis how to start discussion about the long time behavior of solutions. We can construct weak solutions of the problem. The weak solutions satisfy all equations, including entropy inequality. So they are satisfied in the sense of distributions, plus the ballistic energy balance as an inequality. In this framework, we can show existence. So the weak solutions exist for all time. They are global in time for any finite energy data. You can even show, and that's somehow interesting, that actually the temperature will remain bounded below away from zero in terms of the initial boundary data. There is a kind of minimal principle for the temperature, which is very physical, and it's not obvious in the class of weak solutions. With these constitutive equations, you can show that the temperature really remains bounded below away from zero. Unfortunately, you cannot prove the same thing for the density. This is the famous vacuum problem, which is still not solved in the framework of weak solutions. You can show compatibility of these weak solutions, which means that smooth weak solutions are strong solutions, which looks like kind of obvious, however, it's something to do. What is more, you have the so-called weak strong uniqueness principle, which means if you believe the system has strong solution, of course, the system has local strong solutions. This was proved a long time ago in several papers by people like Bari Zarenchkovsky, Bari, or Hamatsumura Nishida. So the system has local strong solutions. However, we don't know if they are local or global. If you believe in global strong solutions, then of course the weak solutions will not give you anything new, because the statement says that actually if you have a weak solution, then it must coincide with the strong solution as long as the strong solution exists. So we have a suitable platform how to start discussion about the long time behavior, because we have long time existence of some concept of solution for any initial data, I mean for any meaning bounded energy. Well, so let me start discussion about concerning the long time behavior of the problem. There's another problem. One, as I said, is existence of solutions out of equilibrium, which we solved by introducing the concept of weak solutions. Another problem when you study the long time behavior, of course, the lack of uniqueness of these weak solutions. The weak solutions, as I said, they satisfy the weak strong uniqueness principle, which means if you know there is a strong solution, there is no other weak solution. However, the weak solution itself, if you have only weak solution, is not uniquely determined by the data, which means that a priori you are not allowed to use any kind of dynamical system theory, which is always based on the existence of some solution semi-group, which assigns to given data the value of the solution at a given time. Still, you would like to study the long time behavior. The way out was proposed by George Searle was by a very nice idea. You simply replace your solutions by trajectories. What I mean by trajectories, well, actually, global in time solutions will live in the trajectory space, which will be actually what was proposed is to consider the space of entire trajectories, which are solutions of the problem, which basically don't depend on the initial data, since they are defined for any time, from minus infinity to plus infinity. And we will see that actually this space plays a natural, this space is actually a kind of attractor for the problem, the suitable choice of this function space. Now, having the trajectory space, you can introduce the omega limit set in the standard way, provided, of course, you have something what is called compactness, which means that you just introduce the omega. Now you replace your individual solutions by trajectory. So instead of working with solutions, you work with the trajectories. Instead of taking value of solutions at the time t, you take the time shift of your trajectory. The time shift is uniquely determined. So from this point of view, we have kind of semi-group, which is now defined on the space of trajectories, which makes it possible to apply all these tools of the dynamical system theory. So that's the idea of Searle. In particular, you can introduce the omega limit set, which is the limit, asymptotic limit. Again, all must be understood in the space of trajectories. Asymptotic limit of one single shifted trajectories when Tn goes to infinity. So this is, for instance, the omega limit set. We will see later that actually the omega limit set is non-empty for the Navier-Stokes-Fourier system, is compact, and it supports some kind of invariant measure. Anyway, what you need is more. Of course, in order to work with this concept, you need global in-time solutions. We have them. What you need is also dissipativity, which is ultimate boundedness of trajectories that I will show. And that's a property which is not so easy to show for dissipative systems, since a priori you don't have any kind of energy conservation. You have only this ballistic energy inequality plus the other equations, but there is no a priori reason why the system should be dissipative. By dissipativity, we will see it on the next line, but I mean dissipativity in the sense of Levinson, which means that no matter where you start with your initial data, After some time, the solution will enter a bounded ball. This bounded ball will be in terms of the total energy of the system. And this bounded ball will be unique for all solutions. So actually the dynamics of the whole system will be restricted to a set which is bounded in your phase space. In order to show something about the asymptotic behavior of trajectories that already belong to this bounded set, you need some kind of compactness property, again, in appropriate spaces. And that's another property I will show you how to prove in the context of Navier-Stokes Fourier. So, okay, so let's go to Levinson dissipativity or bounded absorbing set. This is the result. I will not say anything about the proof of this result. I will just explain what it says. And the proof is based on a very tedious and very long series of estimates that use the ballistic energy, entropy balance, mass conservation, and so on. So as I said, you look for a set in terms of energy such that all trajectories are trapped in this bounded set. Now it is clear that you have to prescribe the mass first, because you have to work with solutions with a given mass, because the mass is a conserved quantity. So you do not expect, of course, to get a bounded absorbing set that would be independent of M, because if M is big, simply rho will be big and you will not enter any finite set. So let's assume that we are given the total mass. And now the statement is that, well, let's take any global in-time weak solution which is defined on the interval t plus infinity. You start at some time t. Actually, from now on, I will not specify what is the initial value, because the initial values now are not really essential. So you take this global in-time solution, and the statement is that it exists a universal constant which depends only on the boundary data and the total mass. Nothing else. So in particular, it does not depend on any initial state, such that the energy of the system, that's the energy now, that's not the ballistic energy, the total energy. If you want, this is a kind of norm I use on my state space, will be less than this universal constant for large time. It's the energy of the system, which of course tells you that actually the solution will be ultimately bounded. This is sometimes called dissipativity in the sense of Levinson. This constant, as I said, depends only on the boundary data. It does not depend on any initial state. Moreover, this time when the energy enters this ball or becomes bounded by this constant is bounded in terms of, say, initial energy. Assuming that the energy when you approach the starting time is uniformly bounded by some constant E0, then you can show that actually this convergence is uniform, meaning that for any epsilon, you will find a time which depends only on this initial energy and on epsilon, such that the total energy of the system, when time is bigger than this, is already bounded by E infinity plus epsilon. This is a result that's surprisingly better than a similar result for the barotropic case or isentropic case, which is the Navier-Stokes system without temperature, when you neglect the temperature. And surprisingly, the system with temperature behaves much better, and you can somehow relax certain certain assumption that you need in the barotropic case. So that's the result that holds for the full system. In particular, it holds for the Rayleigh-Benard convection problem, which tells us that although the solution can be kind of wildly behaving or turbulent, can exhibit some turbulent features, it's still the total energy is finally trapped in a finite ball. And so this is your starting point from studying the long-time dynamics. So from now on, you will start studying the long-time dynamics on this finite ball. What you need in addition to that is sometimes what is called sometimes asymptotic compactness. Again, this asymptotic compactness is a property which is expressed in terms of trajectories. Some people don't like really this line because they say it's a little bit messy. So let me try to explain what I'm saying here. I take a sequence of weak solutions which are defined on some time interval Tn plus infinity, and this Tn goes to minus infinity. So it looks a little bit weird, but I take solution that start at Tn and the starting time goes to minus infinity. So it's like I'm doing some time shift. right? And I assume that uniformly the energy when you approach the starting time is bounded by this constant, by some constant E0, and I assume that the total mass is positive. Then I fix some time interval minus kk, where k is arbitrary. So I focus on a compact time interval. And what I can show that on each compact time interval, the density actually converges to some limit. The limit is strong in the L1 norm. This is important because strong convergence in this norm means that in particular density converges almost everywhere. The temperature converges, I wouldn't say in a similar space, but also in a strong topology of the LP space, and the density converges weakly in the topology L2W12 for any k. And what is more, this limit for any compact interval, of course, you can do it for any compact interval, so this limit gives rise to an anti-weak solution of the problem. So the limit is actually a solution of the Navier-Stokes Fourier system, which is defined for any time, any real time, and has the total energy uniformly bounded by this constant E infinity. Everything would be a kind of obvious if you think about, what kind of estimates you have at n, except the first property. The first property tells you that actually the density converges strongly, which can be an issue because if you remember well the system, there is no obvious dissipation or there is no obvious diffusion term in the first equation, like mass diffusion, which means you don't have, for the temperature and for the velocity, you have estimates coming from the boundedness of the entropy production. In particular, no, the gradient of theta is bounded and gradient of u is bounded. You don't have this information for the density. And so in particular, this tells you that the density does not depend, does not develop any oscillations in time. And that's something you have to work on. And the problem already occurs at the level of the existence theory, right? One of the main achievements of the work of Pierre-Louis Lyons that started a long time ago on investigation of the dynamics of compressible Navier-Stokes system was that actually you can show this, I mean, in the context of isentropic Navier-Stokes, you can show strong convergence on the density. However, you have to assume that, well, for the initial value problem, assuming that the density converges strongly initially, which roughly speaking tells you that, well, the oscillations in the density field cannot propagate in time. Let me point out that the situation is very different here because we have absolutely no information about any initial behavior of the densities and there is no initial time. So proving this is a little bit more delicate, and maybe I should comment a little bit on that. Okay, so the density satisfies the equation of continuity. So from the available estimates we have for the energy, you can deduce that actually the density remains bounded uniformly with values in some L gamma space, where gamma happens to be 5/3. And actually the compactness says that you are compact in this space, which means that you converge strongly in this. And so from this transport equation, this is not obvious. You have to use something else. Because if you look at the equation of continuity, if I write it in this way, what you see on the left-hand side is just a pure transport of the density, while on the right-hand side, you have a term which is rho divergence of u, where you have absolutely no information about any compactness of that. So this term, in principle, can create oscillations. However, fortunately, it's not the case. So how you observe it? First, you consider the so-called renormalized equation of continuity. This equation can be formally obtained from that equation by multiplying everything by d prime of rho. In the context of weak solutions, you have to work a little bit harder. But suppose that we have this equation, and then you perform the weak convergence in the limit. So this should hold for any nonlinear function. Later on, I will show you that actually we have to choose carefully this b to get the result we want. Now we know, now we know that b of rho n converges weakly to some limit, which of course we don't know if it's b of rho because we have only d convergence. And so passing to the limit in the equations, we get this equation for the density oscillation, so to speak, or for the difference between b bar and b rho. For this,
So the idea of Lyon's was actually for carefully chosen D, you can compute the right-hand side of this equation, although it's not really obvious how to do that. And if you assume that this quantity is zero, and if, for instance, at the initial time, and if B is convex, then this will yield that actually this quantity will be zero at any time. Since convex functions are over semi-continuous, this gives you that, well, the limit of convex functions is commutes, which is the weak limit. And if the function is strictly convex, this gives you strong convergence. However, we don't have this information here. So what you do, I mean, your convenient convex function is actually the function rho log rho. So you observe that this has a weak limit, and now you consider what I call oscillation defect, which is actually the integral of the weak limit of this function minus the same function applied to the weak limit. Since this is a strictly convex function, this quantity is always non-negative, and in addition, if you show that it is zero, you get strong convergence of the sequence of shifted rows. So it turns out that what you derive from the renormalized equation is this equation for the defect. Is the time derivative for the defect is actually equal to this term, which is the weak limit of rho dvu minus rho dfu without weak limit. That's now there's a celebrated Lyon's identity, which tells you that actually this quantity is equal to this. This is true in the isentropic case. You can, which means if the pressure does not depend on the temperature. You can show the same in the case with temperatures, since temperature is a kind of constant. But in the isentropic case, you get this inequality, which in particular means that this is a non-negative quantity, which is a kind of miracle, which comes from the equations. It's nothing you can get from the transport equation, which tells you that the defect is a non-increasing quantity in time. So in particular, if we assume it is zero initially, it will be zero forever, and it solves the problem of compactness for the initial value problem. Here, in my context, you show, and there is some work to see it, is that actually this D, the defect, will satisfy this equation. There is some function psi, which is basically the property that it vanishes at zero. It's positive for positive D and negative for negative D. If I exaggerate, it's like D, but it's not D. It's some polynomial function of D. And you can show that the defect satisfies this inequality, but this inequality holds for all time. And in addition, you can also show that the defect is uniformly bounded. Well, this actually implies that the defect must be zero, and this gives you the desired compactness. So that's the proof of compactness. I hope I still have like 10 minutes of my talk, so I can continue. Now I will present some applications of these results. So remember, we know all solutions finally will enter in some bounded ball, and all global trajectories, if you shift them in time, are asymptotically compact. Now you can introduce something which is in Sells terminology trajectory attractor. This is the set of all entire solutions, which means all solutions of the Navier-Stokes Fourier system, which are defined for any time from -infinity to +infinity and have uniformly bounded energy. From the previous two results, you can show is that this term, this set is non-empty. I mean, that follows from compactness and Levinson dissipativity. It's compact because of compactness, and it's obviously shift invariant. Right? So you have this set where basically the whole dynamics is taking place on this set, which is compact, shift invariant, and non-empty. So now you have space to apply abstract tools of the dynamical system theory. For instance, you can prove the existence of a stationary statistical solutions for the Navier-Stokes system, in particular for the Rayleigh-Benard convection problem. Assume that you have a non-empty subset of the attractor of the set A. It can be, for instance, an omega limit set of some bounded trajectory, because all omega limit sets are contained in this attractor by definition, and they are apparently shift invariant, and they are non-empty because of the compactness result. So by shift invariant mean that if I take some solution belonging to this set and I shift it by time, it will remain in the same set for any time. Now you can apply the Krylov-Bogolyubov construction of invariant measures, the classical construction, which tells you that there exists a stationary statistical solution which is supported by the closure of this set. What is a stationary statistical solution? Actually, stationary statistical solution is a measure. It's a probability measure which lives measure nu, which lives on the. It's a probability measure on U closure, which means this is a measure which is supported by entire solution of the Navier-Stokes system. So it supports this. It's a compact invariant set, and this measure is shift invariant, which means if I take a Borel set and I shift it, then the measure is the same for any Borel set. So there's a corollary. Each omega limit set supports a stationary statistical solution. For instance, for the Rayleigh-Bernard convection problem, or in general for Navier-Stokes, for the Navier-Stokes Fourier system with non-trivial boundary temperature. Second, and I think my last application concerns the convergence of ergodic means, which is a partial answer to the ergodic hypothesis that was raised at the beginning of this talk. Can we characterize the time averages of global trajectories? I mean, you should keep in mind that all these results, when I speak about topology, it's always topology of the trajectory space. I'm working on the trajectory space because on the trajectory space, I have a well-defined translation semigroup, which is just translation type. So assume that I have a stationary statistical solution of the problem. We know that stationary statistical solution exists. In particular, each omega limit set supports one invariant measure, which is, or if you want, stationary statistical solution. Now assume that there is a Borel measurable function, well, on this phase space, which is looks a little bit strange because it's a negative Sobolev space. However, for some reasons, we need this space to be Hilbert space, or sorry, to be Polish space in order to apply what is called Birkhoff-Khinchin ergodic theorem. And if he, so natural topology would be, of course, the topology of V convergence, but unfortunately, that's not a Polish space. So you have to do it in this setting. Assume that you have a solution which belongs which belongs to the support of this measure, and assume that the expected value of this, if you want, of this function of the whole measure is finite. Right? At some time, I have chosen the time being 0, but since the measure is invariant, it can be any time. Then the statement is that it is a measurable function from which goes from the trajectory space with the endowed with the measure mu, such that, well, the ergodic averages for all trajectories which are living on the which starts with, if you want, of all stationary all trajectories belonging to this stationary statistical solution, all ergodic means converges to f bar, where f bar is given by this measurable function. So this is validity of the ergodic hypothesis for the Navier-Stokes Fourier system. I must say there is many ifs. For instance, this last result, of course, one should keep in mind that the real ergodic hypothesis would state that this is true for any trajectory, meaning for any global in time, for any solution starting from any data. Here, what we can show is that it is true only on the stationary, I mean, for trajectories that a priori start on stationary statistical solutions. And this convergence is almost surely with respect to the measure mu. So, of course, this is very far from being a definitive answer. What is the global behavior of Navier-Stokes Fourier system? But I think the question in general is very difficult. So, okay, so I hope I convince you that actually studying open fluid systems is much more exciting, since the dynamics is much richer than for conservative fluid systems, and you need much more tools and much more effort to prove some plausible results. However, even in such a bad situation, when you don't have, when you really don't have a problem that would produce unique solutions, and when you don't have problems with apparent a priori bounds, you can still get some results in the framework of weak solutions, which somehow also, in my eyes, justifies that weak solutions have some meaning, at least for the time being, before we get strong solutions, if we get them. Okay, thank you very much for your attention.
Yeah, thank you very much. Yeah, now we open discussions or comment.
So, Eduard, I have a question. Very nice talk. So you mentioned that in the talk you handle the openness from the point of view of the temperature for the Navier-Stokes Fourier. But so you impose no slip boundary condition for the velocity. Have you looked at more general, for example, inflow, outflow?
Yeah, sure. You can do inflow, outflow. I mean, I'm not sure about all these results. Definitely, what we proved is the existence of weak solutions with inflow, outflow, assuming some other conditions. What we didn't prove, and I mean, I guess it could be provable, however, maybe with some technical, I mean, big technical difficulties would be the other things, like in particular the existence of this bounded absorbing set. Because I mean, inflow outflow, of course, it will change drastically the balance of energy, and this would, of course, mean that you need more to work on. But a priori, it is not, of course, excluded. But we didn't do anything in this aspect.
Thank you.
So, and the chat, are there any questions or comments?
Yeah, there is a question in the there is a question in the chat. Oh no, just
Sergey has a
well, I just yeah, thank you. Very good talk, enjoyable. You said that entropy does not add much as far as regular solutions concerned, but for the weak solutions, we have some extras. Would something like this be true also for purely incompressible case, where normally we would just move away from temperature entirely? But
you want temperature but incompressible.
Oh no, let's say, well, I can add temperature for the incompressible equation as well. Just changing the law for the pressure. But the question is, this idea that considering entropy helps as far as weak solution is concerned, will it do anything? Will it add anything? Maybe everyone knows it's, but I don't.
I think there are works for the incompressible case where people, in particular, what I know are people from the group of Josef Malling in Prague, where they also use entropy as a kind of principal state variable because it's better from the point of view of estimates. Here, it's absolutely necessary, since if I use the internal energy balance, there are simply terms I do not control in terms of a priori estimates. I will not control, maybe I can go back to my first slide. For instance, I will not control this term, which looks like innocent, like divergence times pressure, but I have no estimates on pressure, for instance, in the L2 space. I know divergence will not be better than L2, and I have no a priori bounds. So the entropy is I mean, I don't know how I would formulate, I don't know how to prove the existence of weak solutions for this, in this formulation. So the entropy, the advantage of entropy is that you get rid of these terms. And also it gives you, I mean, the weak formulation, I didn't write it down really what it is, but it's convenient to write it in terms of entropy because you gain this weak strong uniqueness principle that you would not get if you write it only with the internal energy, because at the level of weak solution they are not equivalent, right? I mean, you have to choose what you want, and the entropy is really convenient. And I think it goes back to the ideas of Godunov, who in '60s proposed somehow to build up everything like starting with entropy and then maybe adding some kind of energy balance. And so this approach, I mean, you may not agree that that's optimal from the physics point of view, but mathematically it's very convenient, and it's the only way I know that you can construct the weak solution. I don't know how to get a priori bounds from any other formulation. I really need that, especially for the open system. Of course, for incompressible, it could be different, right?
Yeah, divergence is zero.
I think that I think that if you're close to an adiabatic state, you know, the entropy, the temperature, and the density are sort of, I mean, they're not in the, you can use one or the other, but you have to be close to, in the incompressible case, I mean.
Yeah. No, here the amazing thing, at least, but you tell me if I am wrong, but the only estimate you have at hand, I mean, if you prescribe a boundary temperature, is this inequality. And if I plug in really something like standard Boyle-Marriott law, I even don't see any a priori bound whatever for this system. Any a priori bound except the mass conservation. Maybe you tell me I'm wrong, but I can't get it. Of course, there are results on local existence, but they are done in a different way. I mean, they work with energies. I mean, they are local in time, so everything is linearized. And but here, of course, we do not want to linearize since we are not close to equilibrium. And this inequality doesn't. I mean, I don't get any kind of estimates, any kind of a priori bounds, even something like energy will be bounded. Nothing. So I have to use this. In particular, you see that the entropy is convenient because you can get rid of these boundary terms and you gain this entropy production term on the left-hand side, which also gives you some estimates, which means provided you control the right-hand side. Yeah.
Okay, thank you.
Okay. So is there some?
Are there some questions?
Yeah, actually, it's not a question, it's just a
It's
thank
only
you.
thank Okay, thank you for staying till the end, especially Hideo.
Well, I can ask questions forever. You know, I have more, but time
Any other
probably.
comments? Any other comments? Okay.
Okay, if possible, one more question. The last one, I promise.
Yeah, please.
Yeah, go ahead.
Again, that might be that I misunderstood here, but it looks like we have in this case a proof of the compactness of what we in my field called the turbulent flow attractor.
Yes.
That is this invariant set, whatever you call it there. Would that be also true for an incompressible case?
I think yes. I think there are results for incompressible case, of course.
So
Again,
this idea of
why
time running all the way down to minus infinity does this. And in what space?
This, I mean, George Sell actually was the first who did it for 3D Navier-Stokes incompressible, right? That was his idea, how to handle like attractor problem for 3D incompressible, because in 3D incompressible, you do not have uniqueness of solutions, at least you don't know. So he came up with this idea of anti-trajectories. Later, as far as I know, there were also people like Nečas in Prague who were using the technique of short trajectories. I mean, the idea is that you take somehow time into account and you work on this trajectory space. It also goes back to stochastic equations. I think there's a paper by Ito where he studies stationary solutions, stochastic solutions, stationary solutions, stochastic stationary solution. He also introduces this space of anti-trajectories. It's kind of convenient, right? And at the end of the day, you get basically the same answer, like you get compactness. Huh? The advantage is that now your semi-group, I mean, it's a time shift, which is a unique operation on the trajectories. So you can use all these standard theories of Krylov-Bogolyubov or Birhoff-Kimchin, because you have translation semi-group acting on a compact space, which is great.
Thank you very much. Excellent talk. Thank you.
Okay, thank you very much for coming.
Okay, are there any other questions or comments?